Thanks to all of you for being here. And it's great to be at University of Minnesota and visiting the Minneapolis for the first time. So at any point, feel free to interrupt me asking questions. So this is a seminar. So there is no point of covering, I have 39 slides. I'm okay with covering the 25 of them, but as far as we all understand the main contributions and what is important from take away from these results, okay? So as Yashong mentioned, I will focus on min-max optimization and some convergence guarantees and practical performance. So I could have named this talk any of these three choices based on the backgrounds of the audience. I choose min-max optimization because I believe is something in between the machine learning world and the optimization literature. So all the results that I will present, if you come from applied math background, are related to variational inequalities, a tool that can capture min-max optimization and minimization problems as special case. If you come from a machine learning background, then we can easily have it as multi-agent learning when you have multiple players compete with each other and try to reach an equilibrium. So any of this is the same kind of problem, can formulate under the same umbrella. And the min-max optimization is the most popular way of represent each one of them and the most simple way of understanding the contributions in terms of algorithmic design and equilibrium perspective. So let us start. I will start with some introduction where I will introduce why the multi-agent learning and min-max optimization are under the same umbrella. Then focus on the motivation of solving these problems and some open problems in the area. And then we will focus on two main algorithms, stochastic gradient descent ascent and stochastic extra gradient. Both of them are in the stochastic setting because we are in the very large scale regime. So the deterministic methods are not able practical. They are very expensive to run. So we like the stochasticity as a tool and the randomization as a tool for solving large scale versions of the problem that we care. And then the two main parts are some recent advances on the stochastic extra gradient and how we can use it efficiently for solving min-max optimization problems and large-scale multiplayer games. And then the second part is the federated learning version of it, where we will explain the background on federated learning and how this can be extended to solve multiplayer games. So this second part is the last, as I mentioned, 10 slides of the presentation. I'm very happy if we cover the first part and do that properly. So feel free to ask as many questions. If we have the second part, have more time, I will cover the second part as well. It's the more recent output of our group. So as we know, in minimization, we have to find a minimizer of a function f of x under some constraints x. And this appears in many applications, including finance, operation research, engineering. And in particular, the main focus of my group as understanding this kind of problems in machine learning framework and data science. And we focus on applications related to visual object recognition, speech recognition and natural language processing, personalized recommendations, sensors in autonomous cars, and of course, the training of deep neural networks. All of them can formulate as a version of this minimization of f of x, where typical this f of x is stochastic, is in expectation. And we try to solve this problem. However, the recent years, we have many examples of machine learning problems that cannot express as a minimization problem anymore. So some examples are the generative adversarial networks or GANs, the AlphaGo in DeepMind, formulations in reinforcement learning, domain generalization, adversarial training, and goes on. All of these problems the last decade has one common feature, that instead of trying to minimize a function, we try to find the equilibrium of this min-max optimization problem, where the minimization is a standard minimization problem that we had before, and the maximization represent robustness of your model, fairness of your model, the adversarial training of your model, and goes on. And this equilibrium computation, which I will explain in more detail what is the goal of this problem, is more challenging task than the classical optimization. So the classical algorithms that we know does not necessarily solve this problem in an efficient way. So we have these machine learning applications, we have the modeling that everybody have in mind, But typical practitioners, what they do, they run classical methods that we know from the optimization viewpoint for solving these problems. In theory now, from optimization side, there are extremely rich literature for solving min-max problems and games from 30 and 40 years ago, typically in the deterministic setting, where we have the forward-backward algorithm or the gradient descent-ascent method or the extra gradient method. And we have this practitioner's viewpoint, machine learning applications, and we have these theoretical results from many years ago from optimization literature. And what we try to understand now is how we can take these results and popular algorithms that people already know and analyzed many years ago and reformulate them, have new variants of them for solving the practical problems that we have in machine learning applications. So in that scenarios, we care about understanding the structure and properties of these modern problems, explain the behavior of existing popular methods for solving the same class of problems, but under the new assumptions. They might be non-convex, they might be non-smooth, they might be stochastic. So these algorithms, they don't have convergence guarantees anymore. And then we try to propose new algorithms with convergence guarantees for these classes of problems from machine learning perspective. And the last few years, we spent a lot of time on doing exactly that. We propose stochastic Hamiltonian gradient methods, stochastic gradient descent-ascent in different convergence guarantees, in different practical performance. We have the convergence of stochastic extra gradient algorithm in different scenarios and different practical applications that appear in machine learning setting. The stochastic gradient descent-ascent again with a unified theory understanding in different settings, different update rules. And then we move also to the federated learning and distributed setting of designing methods that solve variational inequalities, but themselves can correspond to min-max optimization as well. And in this talk, what we will focus on are solving this min-max optimization problem, where for simplicity in terms of notation, I will have as X the concatenation of the two players' action, and as Fi, the concatenation of the partial derivatives with this sign minus here to represent the maximization problem as well. So this is a partial derivative of the minimization player, and this is a partial derivative of the maximization player. And having this notation in mind, the stochastic gradient descent-ascent can represent with this algorithm here. And what this method does is that it takes the gradient descent of the first player, gradient ascent of the other player, and move towards the negative direction of this operator. And we have this step size that we need to tune. This is the most important parameter that requires special tuning for the conversions in different scenarios. So that's one of the methods. And the other very popular algorithm is the stochastic extra gradient method. As the name says, extra gradient method computes an extra gradient in every step. So we start from the standard gradient descent-ascent, and we use the xk hat as the starting point of the next part. And we call this extrapolation step, and this is the update step. And this is the stochastic gradient descent-ascent and stochastic extra gradient methods. At the moment, I will consider these two the most popular methods for solving any version of min-max optimization problem in machine learning applications. That in specific ways, you sample your operator, and you use this operator with different step sizes, gamma k and omega k, to find the equilibrium of a stationary point based on the applications that you have in the machine learning scenario. So these are the two methods that we will focus primarily in this talk. Are the update rules clear? Are very simple. I didn't go into the convergence guarantees yet. This is what the algorithms look like and the ones that we will focus the whole presentation. So this is now in terms of practicality and open questions, these are the methods that practitioners use. From theory side now, and this is what we care a lot, is understanding some open questions related to mini-batching. How large is your mini-batch size? This efficient step size selection. What should be these update and extrapolation steps for having conversions that you want in a very fast convergence guarantees, a fast conversions in a smaller neighborhood with reliable convergence guarantees and generalization performance, what the machine learners care. And of course, we care about various sampling strategies, and ideally without very strong assumptions, like bounded gradients or bounded variance. That's our goal, the open questions that we will try to resolve. And this work is a joint work with Sayantan, Konstantinos, and Taiho. All of them are at Johns Hopkins University. Sayantan finishing next year. Konstantinos is a third-year PhD student, and Taiho is a postdoc in my group. And for doing that now, for answering all of these questions, let us formulate the problem a bit more different in terms of notation and in terms of goals, because as I mentioned, variational inequalities is just a way to represent the min-max optimization problems in a more coherent and more clear way in terms of notation and convergence guarantees. So we will use this kind of problem, and this is what we call unconstrained stochastic VIP problem, where our goal is to find the X star that makes this operator F equal to 0. And we assume that this operator is just a finite sum of Fi operators, where we have n different components Fi. So this is a very simple problem. We call it unconstrained stochastic variational inequality. This is what machine learners use. But if you come from applied math, this is just a system of nonlinear equations or a root finding problem. All of them have exactly the same formulation. We use the variational inequality aspect, and the problem is not inequality. So this is a weird terminology, but this is an unconstrained version of what we will see later in its full format to be the unconstrained stochastic variational problem. And why this is interesting? Our goal is to solve this min-max problem, where we want to find this X star that is the equilibrium of this min-max optimization, which means that we want to find the X star that minimize the function f with respect to x1 and maximize it with respect to x2. And we can see that this problem, if we go and use this notation that I explained before with the partial derivatives, then one can see that solving the VI problem, that is finding X star that makes this variational problem 0, is equivalent of finding a stationary point for this problem here. And here, stationary point is a point that makes the gradient equal to 0. And if your problem, the min-max, have extra structure, being convex concave, then solving the original problem can translate to find a global min-max solution of the min-max optimization. So that's the connection that we will use. And the takeaway message from here is that if you have this problem, if you reformulate in this potentially more simple variational inequality problem, we are able to do something more about the convergence guarantees. And more generally, this VI problem can formulate an k-player game where you, instead of having 2 players, you can have multiple players trying to reach equilibrium. And the corresponding variational inequality will have a different Fi that corresponds to the concatenation over all the gradients that you have of all players. So that's the main connection that we will use throughout the presentation. Now, in terms of assumptions now, before we run into convergence guarantees, we need to understand what the operator and the min-max optimization problem satisfies. And we call this operator quasi-strongly monotone if this inequality here is true. So we assume that you have a given solution X star for which you have the inner product of f of x, x minus x star, being lower bounded by mu times the difference of the x minus x star. And here, this assumption is called quasi-strongly monotone in the literature, but captures all strongly monotone VIs. This includes strongly convex, strongly concave problems, or star strongly convex, star strongly concave min-max optimization problems. It doesn't imply that you have a unique solution. So you can have multiple equilibrium. And it has many names. It's called strong coherent VI or strong stability condition. Or if the mu is equal to 0, then you have the variational stability condition. So all of them appear in different applications. It has different names. And this will be our first assumption for which we will prove something. And Then the second assumption is what is now popular as weak minty VIP, where we have the same inner product at the left-hand side, and now we are lower bounded by a negative quantity. So we have minus rho, the norm of the f of x. So if it was monotone, then this rho will be 0. So this weak minting has, again, many properties and appears in different scenarios. For example, we can have all the minty variational inequality problems as special case, includes all the monotones are special case. And when we go to the min-max optimization setting, this includes many non-convex, non-concave games as a special case. So it's a way of reformulate. As I mentioned originally, we have the machine learning applications, and we try to understand in what scenarios of these machine learning applications our algorithms have convergence guarantees. At the moment, this weak min-p inequality is one of the most relaxed conditions that allows us to do that. That we can go, and if we assume that happens to be true in several scenarios, then you can have convergence guarantees. To understand where this belongs in terms of assumption, if you're familiar with minimization problems, and you know strongly convex convergence guarantees, the last 5 to 10 years, people use this Polyak-Loizou inequality as an alternative to strong convexity to prove some convergence in the non-convex regime. This is the corresponding of this, of the Polyak-Loizou. You want to make assumptions on the structure of the non-convex problem in order to show something in terms of convergence. And this is where this weak minting belongs to, and the strong, quasi-strongly monotone condition that I mentioned before belongs to as well. And what we are aiming and what assumption we will make throughout the presentation, which is not necessary for several of our results, but at least for this presentation, I will assume that the FIs are all Li ellipses, that they have the operator to be upper bounded by Li times the difference of x minus y for each x and y that belongs in the domain of the problem. So before I move on, is it clear the setting that we're focusing on in terms of assumptions? Any questions about their practicality? No? Okay. So now we will present the next 3-4 slides will be on some tools that will allow us to analyze the methods that I explained before, the stochastic gradient descent ascent and efficient variance of stochastic extra gradient in a more easy way for understanding the different sampling strategies. So as I explained before, our goal is to find an X star that makes this equal to 0. So what we do instead of solving this problem, we propose using these sampling vectors, which is the V of n different components, follows n distribution D, that makes each of the coordinate in expectation to be equal to 1. And we reformulate this problem with something equivalent now, that is the expectation of this D, that's a user-defined distribution. And we define this FV to be the concatenation of many of the FIs. That's the definition. This is how we define it. Now, why this makes sense is because this D is something that we control. And we claim now that if you go from the original problem to this new problem, you are able to analyze any sampling strategy for the algorithms that they will come later. So I explained stochastic gradient descent ascent or stochastic extra gradient. All of them, typically they use uniform sampling to make the update rule. With this way, we are able to control the sampling strategies. And this FV, which is the concatenation of this FI, a merge of different FIs with different weights VIs, are still an unbiased estimate of the true operator. And instead of solving the original problem, now we solve this stochastic reformulation problem. And our goal is to find this X star that makes this expectation with respect to this D distribution of the FV of X star equal to 0. And this is what will be the focus of the presentation. Now, why we do that is because if we go into the update rule, we are able to control the D, and with this way, this D encodes any mini batch strategy any non-uniform sampling as well. And we perform general analysis for any distribution D. This stochastic reformulation is a tool that used extensively in different literatures. It uses stochastic optimization in methods for solving linear systems, in variance reduction methods, in adaptive methods. Now we use similar tools for the min-max optimization. It's just a tool. Now, as I mentioned before, the main issue of extra gradient is that it requires this extra gradient in every step, that every iteration of the extra gradient method requires twice computation compared to the gradient descent. So to alleviate this problem, the community used this stochastic fast extra gradient method, which is the stochastic extra gradient, but now we use the previous computed iteration, and we avoid in that way to have twice the computational expensive iterations that we have for the stochastic extra gradient. So this method is also known as stochastic optimistic method. The reason that I highlight the past version here is to make sure that we understand what is happening. In the previous setting, in the standard stochastic extra gradient, in every step, you start from the xk, you compute the xk hat, and you move to the next iteration. Now in this part, we use this xk hat minus 1, which is the previous saved iteration of the previous algorithm. And by doing that, you have a very cheap iteration, but you have all the benefits of the extra gradient method. And now, having this method as a starting point, we are able to control, using the stochastic reformulation, how we sample this FVK in the aptitude rule in order to have meaningful convergence guarantees. So before I move on, is it clear so up to this point, we explained the assumptions that we will focus on. We explained the aptitude rule. And then why this VK that follows this distribution D is something that is a user-defined distribution that allows us to analyze any possible sampling strategy as an input to the algorithm, that you can have uniform sampling, important sampling, independent sampling. Any of these will still work. In several scenarios, in deep learning as well, we have non-uniform sampling that you can force your algorithm to select in order to have better performance. So this is just a different way of representing the problem that allows you to control this distribution D as well. So, and to explain in more details what I mean, I will not focus so much on the technicalities, but the important thing is that if you have, for example, this mini batch sampling, where in every step you sample uniformly at random a mini batch, then the aptitude rule itself will have this format here, that in every step you go, you select your mini batch and you move towards this direction. It might look surprising, but at the moment we don't know how this tau, the mini batch size, should be selected in order to have better performance. If the tau was equal to n, then we have a full deterministic method. If the tau was equal to 1, then you have the standard stochastic method that you select single element sampling. In practice, people go and say this tau should be 256 or can be 198, but there is no explanation behind it. They just select the one that generalizes their adversarial training better. So with our theoretical results, we try to understand what this tau should be in a closed form expression in order to understand if this problem satisfies this weak min-t, or if this problem satisfies the quasi-strong monotonicity, what should be the mini batch size. And for doing that, we want to understand the assumptions of the problems in terms of stochastic noise. Again, up to this point, we cover classes of problems. We didn't explain how the stochasticity is introduced to the method. And this is what we do in this slide. So we introduce this expected residual condition, which essentially is not an assumption, but is an inequality that's satisfied always when the FIs are Li ellipses, the assumption that we make throughout the presentation and throughout this line of work. If you have Fi ellipses, then you can prove that this expected residual is satisfied with specific closed form expression of the parameter delta. And what we do now is that having this expected residual, we are able to bound the stochasticity. This G of X is the unbiased estimator of in every step. So this stochasticity can be bounded using this expression here, with delta have a closed form expression, and this sigma star being the variance of the optimum, the variance of the stochastic noise at the optimum. So all of them are not anymore an assumption. It's not like the bounded gradients or the bounded variance assumption that you might have used to in a stochastic algorithms. Now we have a specific bound of the stochastic noise that is not related to an assumption. It's a condition that always is satisfied, and this delta can have a closed form expression that is related to the ellipsis constant, and this sigma star have, again, a closed form expression. So it's not something that you need to assume. It's a condition that is satisfied for free. Okay? Now, all of them, again, are technicalities that will allow us to have convergence guarantees. If you're a practitioner, you might not care of any of those, are very theoretical oriented. The stochastic reformulation and this assumption here is for us to understand the properties of the algorithms. But now, if you care about the actual practicality of the method, then this delta has a closed form expression that we show that here as well. And we implement the methods using this information, okay? And let us go into some of the details of how this assumption makes sense. So if you are from theory perspective, then you might have seen before bounded operators or bounded variance as an assumption in the stochastic noise. All of them are very strong conditions that rarely are satisfied in practice. You cannot assume that you have bounded gradients. If you say that your problem have a stochastic gradient that is bounded, then essentially you make it a constraint optimization and you project into the bounded domain. But in our case, we do not have this anymore. This is very strong. And we can show that this inequality 10, just to go back to make sure that this inequality 10 that we have here is the most relaxed condition that you can have probably. And this is what we use. And it's not a condition. Is something that always holds for free if you have the FIs to be Li ellipses. Okay? So let me, again, pause here in case that something is unclear before I dive into convergence guarantees and practical performance. Is any of the tools that we use unclear? It might be a lot of information. We explained the stochastic reformulation for us to allow to have different sampling strategies. That's one. And then because in the stochastic setting, you need to somehow control the noise, we are able to control that with this expected residual condition that allows us to have an upper bound that is obtained for free when you have Li ellipses operators. Okay? And now these tools will be our starting point for analyzing the method with applications in machine learning. Any question about any of the tools? Okay. Now let us dive into some convergence guarantees. That's the most important thing for people wanting to solve min-max optimization problems. So we have this update rule. This is the standard stochastic extra gradient that I mentioned before, just written in one single line. There we have the extrapolation step and the update step. Gamma k is the extrapolation step size, omega k is the update step size. Now what we do is that if we make the assumptions that we explained before, and we go and select the constant step size to have this format here, and or this format here, we have constant step size selection, or somehow a switching step size selection, where you first run constant step size for a specific number of iterations, and then you pivot to a decreasing step size once you reach the neighborhood of conversions to achieve higher accuracy. Now, once we have those, then we are able to guarantee either a linear convergence to a neighborhood of the equilibrium point, or we can have sublinear convergence to the exact solution. This is not something that we don't expect. This is exactly what we expected under this quasi-strong convexity that I explained before, quasi-strong monotonicity. The interesting part now is that these step sizes, the constant and the decreasing, depends on quantities that are related to the sampling strategy. So if you select different mini batch sizes with different sampling in each of them, then the step size themselves depends implicitly on this delta, where the delta was a function of the sampling that we explained before. Different samplings, different delta, different samplings mean different step size selection. And this is the novelty of the whole approach. As the mini batch size increase, the step size should change. And if you have decreasing step size, then the neighborhood of convergence will be affected from the mini batch size. So this is very informative from practitioner's viewpoint. You have mini batch size, that is the main parameter, that controls the step size selection and itself controls the neighborhood of convergence. And we are able to very easily identify the issues that previous analysis might have, and now resolve them by explaining what is the mini batch size that you should run, what is the step size selection that you should use, and what are the convergence guarantees that this method can have in these practical scenarios. And the most important thing, and this is rare in the stochastic setting, is that all of our methods, because they do not assume this bounded gradient or bounded variance condition, obtain the deterministic state-of-the-art analysis as special case. So if you go to the deterministic extra gradient method, and you see how this method behaves under this scenario, from 30 years ago, the results that I explained in the first slide of this presentation, if you go to the original Karpelevich paper and try to change the analysis that she had into the stochastic optimization setting, is not possible without making the assumptions that we make. And we are able to obtain the convergence guarantees that they have from 30 and 40 years ago as a special case, showing the tightness of the stochastic regime and how we can actually control the deterministic results as well. Is that clear? Okay, good. So, and just to show you an example, this is the most simple example that you can imagine, but we can start from this before we move into more challenging settings. Here we have a strongly monotone quadratic game where you have to find the equilibrium of this expression here, where the AI is the matrix that are control the player one, the CI is the matrix that controls the player two, and this BI is the intersection of the two players, X1 and X2. And what we can do now is to run the methods. So our theory suggests exactly what we see in practice. So if you run the methods with constant step size, then we can see a convergence to a neighborhood of solution. You start from one point, you reach a neighborhood, and then you stop there. You cannot go closer and closer. And our theory suggests exactly the point is this green dotted line that you need to pivot from a constant to a decreasing step size if you care about higher accuracy and higher and smaller neighborhood of convergence as the algorithm progresses. Of course, this is a sublinear convergence, is slower, but this is expected. But now we are able to know exactly the point that you need to change from constant to decreasing step size, and this point changes based on the mini batch selection that you have in your method. And we explain with closed form expressions when this will happen. And another important aspect that it was very underexplored, at least in the last 2 years, the community starts caring about, is that in the stochastic setting for solving minimax problems, everybody uses this uniform sampling. Uniform sampling is when you go and with probability, let's say 1/n, you select one of your components. But this is suboptimal, and you need to select and give different probabilities to different mini batches. And we are able to highlight what mini batches are more important than others. And we run with these important, potentially standard probabilities of the different mini batches in order to improve the performance of the model. Again, this is convergence guarantees. We do not have anything yet on generalization performance. It's just to verify that the theory that we have is tight and makes sense in scenarios that even now we didn't know how the method behaves. So here I just highlight one more time the difference on the step size selection and the important difference on the sampling strategies. And the sampling strategies are controlled by this distribution D that is user-defined distribution. Okay. And then we can move on to, and here I will just go quickly through it. I want to highlight only one aspect. This weak minting is the most relaxed condition for which we can have convergence guarantees at the moment. So we have highly non-convex, non-concave problems in machine learning settings. For those, we cannot really say anything about the methods. The weak mint is the most relaxed condition that the community came up with for which we can have convergence guarantees. Now, the issue that this condition has in the stochastic regime is that it requires large batch sizes. For the method to have convergence and being able to prove something, we want this mini batch size to be quite large and essentially have the method behave implicitly as a deterministic method. So this is a negative of any result that exists in the literature. And in the next few slides, I will explain a way that this issue might be alleviated, not having the batch to be large in order to provide convergence guarantees in the stochastic setting. And here we provide the standard convergence of 1/k for this kind of problems. So it's not surprising. Again, the main contribution here is that we have control of the mini batch, control of the step size, and control of the sampling strategy. So this is not very common in the stochastic setting. People simply assume uniform sampling, or they assume constant step size that depends on 1/L. Here we change how these are selected, and we have more practical performance on this. So, and of course, the most important aspect is that for the deterministic oracle, when you have deterministic setting, again, we obtain the state-of-the-art analysis that appear in the literature from a few years ago. So there is no difference in terms of having a stochastic analysis versus having deterministic. There is no drawback on this. And up to this point, just summarize, and then I can take 1 minute in case that you have any questions about the takeaway message of what we covered up to this point, is that we explain this SPEC, which is the Hash stochastic extra gradient, that doesn't require this double operator evaluation. And with our analysis, we provide answers to what the mini batch version of the method looks like, how you can control the mini batch size, the efficient step size selection, because it depends on the sampling strategies, we are able to control and have different step size for the method to converge efficiently under different scenarios. We have the sampling strategies that I mentioned before, and we focus on two of the largest at the moment classes of non-monotone problems. Non-monotone here refers to non-convex, non-concave. There is no point in the whole presentation that we assume that the problem is convex concave. So we don't have such concept. We make an assumption, quasi-strongly monotone and weak minty, for which we can still have a concept of equilibrium, but the assumption is the problem is non-convex, non-concave. So if you are in the, let's say, adversarial training and or robustness of your model, and you represent this as a min-max optimization, if you go and somehow you show that satisfy this weak minty or the quasi-strongly monotone, which still now is very strong assumptions, but if you manage to show that and explain the scenarios that this is satisfied, then we have convergence guarantees that are meaningful, that can control in different scenarios and different parameters. And the practical now implementations of this SEC, and this will be the focus on the next few slides. If you go to PyTorch implementation or any TensorFlow implementation for adversarial training. Then you have randomly reshuffle of your components. So you don't uniformly at random select them. When you train a deep neural network or the adversarial training, you shuffle your data, you use them, and then you might shuffle them again and use them again sequentially. But this is not captured by what I explained up to this point. The next few slides, we will explain how whatever I explain now can be extended in a more practical way to explain this practical behavior of shuffling the data and the benefits that you have by this shuffle over the uniform sampling. And this is a paper from this year that we focus on understanding the extra gradient methods with this random reshuffling. And we have different convergence guarantees and actual practical implementations in different machine learning scenarios showing exactly why the shuffle should be preferred over the uniform sampling. So before I move on and explain the differences, any question about whatever we cover up to this point? Either the takeaway message that I just mentioned. Yes, please.
Could you go back to slide 19, please?
Slide 19.
Yes.
Yes.
So on this graph, the uniform sampling and the important sampling, will they eventually reach to same level of conversion?
So yes, so if you eventually run this, let's say instead of 1,000 iterations, you run it to 1 million iterations, then both of them will still converge to a neighborhood of the solution because the method is stochastic. They will not reach the exact optimum. What we claim is that with important sampling, the neighborhood of conversions will be smaller. Is that clear?
Yes.
Okay. Any other question? Okay. So then let us move on to the random reshuffling variant. So the stochastic extra gradient, as I mentioned, is the algorithm that you see there. In every step, we sample the FI, we use it to compute the XK hat, and then we use this XK hat in this update rule to obtain the next iteration. The reason that people use extra gradient is because the gradient descent diverge for something beyond strongly convex and strongly concave. That's the whole reason that this algorithm is important to analyze in these scenarios. Now, when you have finite sum problems, finite sum is this expression that instead of having expectations, you have n different components that you sum them, you take the average, and this is your problem. If instead with replacement sampling, we have random reshuffling, what this method looks like is that you go and you run the method for the first epoch, and you might select this different order of the components. You start from the n, then to the n minus 1, up to n. Then in the next epoch, you reshuffle your data. You reshuffle these components. You have a different order of them, and then you go through this order sequentially. And then again, you randomly select one of the different permutations. And again, you reshuffle the data, you select this permutation, and you do that sequentially. So this is a big difference compared to the uniform sampling. The uniform sampling has unbiased estimators. If you do the shuffle, you don't have unbiased estimators anymore. Everything becomes biased and the analysis might be more challenging. But this is what people actually run. And what we notice, and of course, these RR ideas, the random reshuffling, are very popular in stochastic gradient descent and standard minimization problems. And there are multiple papers the last 4 or 5 years that try to understand this phenomenon. Why? By shuffle the data, you have better performance over the uniform sampling. The same things, just blindly, practitioners used in min-max optimization and all the applications that I mentioned before. Generative adversarial networks, robustness of machine learning models, they use the shuffle by default. And now we try to understand, okay, in this scenario, can we understand the methods and how they behave under this shuffle strategy? And I will just present the method here quickly, is that in each for loop, we sample a permutation. And once the permutation is selected, Then we do the update rule similar to what we have seen before, but now with the first element of this permutation, then the second element of the permutation, and goes on. And now the main question that we try to answer is, can we have better theoretical and practical performance of this stochastic extra gradient with the reshuffling? And the answer is yes. And there is very distinguished performance in terms of trajectories in min-max optimization problems. So here we start from the starting point, and here we have the equilibrium, a very simple problem. But what we notice is that when you have this shuffling thing, the cycle of the trajectories, instead of being large and then rotate around the solution to find equilibrium, this shuffling moves the direction of the gradient to be closer and closer to the equilibrium. And this allows you to have faster method, because the cycling, at least this is the intuition behind why this works, is that the gradient points towards a direction that is closer to equilibrium. It avoids these circles that you might, some of you being familiar, if you train min-max optimization problems, you always see these trajectories in the gradient directions that take place. Now, if we have this error, then this random reshuffling always converges to a smaller neighborhood of convergence. And we managed to show that provably in different scenarios. And here we focus on different settings. They have strongly monotone and affine, and monotone problems. And we compare the iteration complexity. I will not focus so much on the theory in this presentation. I just want you to understand the main takeaway is that in the strongly monotone and affine scenario, affine is when the operator has this essentially linear system behavior. Then after a certain number of epochs, then this SECAR is always has better iteration complexity compared to the non-random shuffling variant. You have this big O behavior that is always better when you have large number of epochs. This K is the number of epochs of the method that you run. So this is very theoretical oriented and the analysis, but this can be shown in practice as well. So when you have strongly monotone or affine problem and you use random reshuffling, then you have faster performance. And another important aspect, and this is what I mentioned before as a drawback on the analysis of standard stochastic extra gradient methods, is that they require this large batch size for proving conversions. If you do the trick with the shuffle, you are able to avoid these large batch sizes. So you can converge even with small batch sizes to the same solution. This is an artifact of the proof, but we can see that in practice as well. You run the method, you don't need large batch sizes in the monotone scenario to have conversions. You still converge with small batch sizes. You might have larger neighborhood, but that's okay, this is expected. But at least theoretical, we can avoid this limitation that the standard uniform sampling version have. Okay? And we ran in several experiments this kind of behavior. In several experiments, we notice this kind of behavior. We have strongly convex, strongly concave. We have bilinear problems. We have some adversarial training examples as well. In all of them, we can see that here the orange line is the main thing to focus, that using RR, we are able to converge to a smaller neighborhood of convergence without any extra effort. Is that this is the reason that most likely the practitioners, they use shuffle in the first place, is they want, with the same effort, with the same computational expensive calculations, to reach to a high accuracy of the solution without compromise the behavior of generalization. So here they converge to the same point. There is no reason to converge to a different local stationary point, for example. But they still achieve that using this shuffle trick. Is that clear? The motivation of why the shuffle might be helpful in theoretical behavior?
So yeah, I do have a question here.
Yes.
Yeah, I know that practitioners are using this, but I mean the time they start to use this, they definitely definitely didn't think about anything about the, theory here.
Yes, of course,
Because
of course.
it started very early, right? My understanding that why people come up with this, I think two reasons. One is that they think about the efficiency of fetching from memory, because on computer memory, when you try to fetch from consecutive blocks,
Mhm.
it tends to be much more efficient than you try to fetch from random locations. And I
Yes.
think that's one reason.
Mhm.
Another reason is that, just intuitively, if I do this kind of sampling with replacement,
Mhm.
there's a small but considerable probability that I miss out some points, right?
Yes, yes,
In each
I agree.
block,
I
right?
agree. Mhm.
Is that also the intuition why theoretically we can prove better result here? The second
Yes,
one.
I think so. So
Okay,
the
so
main,
it's through some
so you
very
can,
careful probability analysis.
yes, yes. So the
Okay,
main,
okay.
I think the main output, at least from the theory side, is that you can imagine this random reshuffling idea because it goes through all the data. So you don't uniformly at random select, and some of them might not be selected at all. Because you go through all the data, essentially it behaves like implicitly as a deterministic method that can see the whole spectrum of the full batch variant. And by doing that, you are able to control where you will go in terms of direction better than the non-uniform than the uniform sampling. I think that's that corresponds very nicely to what you mentioned, I think, but it is the same kind of narrative that if you do that, you have more information as the algorithm progresses. Any other question? Okay, so I think we have another 5 minutes or 10.
Yeah, another 5 minutes.
5 minutes. So this is the main part of what I wanted to cover, but let me devote another the last 5 minutes just to summarize what the takeaway message is, and slightly mention 2 slides of the new results that we have in the federated learning setting. So as I mentioned, the takeaway message is that we have tight analysis and improve using this with replacement sec variants. We have future extensions that we're currently working for this standard VIP setting where you have actually inequalities instead of equalities. And for all of those, or for this kind of work, we have also these GitHub repos that you can go and you just use the methods that we propose as black box for understanding and understand the behavior in different applications. It's just the algorithm there. You can call them and run it, any experiments for min-max optimization to see from practical viewpoint if they work. Now let me go to, and this is, I will mention it briefly, it's very recent line of direction that we are focusing on. So I will just devote 2-3 minutes for you to understand the main idea. Up to this point, we solve these min-max optimization problems or the multiplayer games without assuming that the communication between the players is a bottleneck. We assume that we have access to all the players, and these players communicate with each other to reach an equilibrium. Now, in practical scenarios, if the players are nodes in a distributed system, then they cannot assume that they can communicate for free. They need to exchange information, and they need to exchange information in a meaningful way and as cheap as possible. So in that scenario, we introduce this multiplayer federated learning setup where we try to solve equilibrium problems. As I mentioned already throughout this presentation, find this min-max solution, or if you have multiple players, find the equilibrium point. But now the main selling point and the main challenge is try to do that with as less communication as possible. Okay? And we claim that this scenario might have applications in energy, some economics problem as well, healthcare potentially. We don't have the full range of applications ready yet. We understand the theoretical side, and we try to see how this behaves in practical scenarios. So I will skip the first 2-3 slides, I think, just for, it is mainly for some of you that you are familiar with the concept. We have in the standard federated learning, we have this problem where each of them has one FI, and they communicate to solve this minimization problem. Then the community went and they extend the whole idea to algorithms for solving min-max problem, where now each player has access to X and Y. Now, what we are suggesting is that instead of doing that, our setting is that the players themselves have their own function, and now they communicate their strategy. And they do that only after a specific number of iterations. And this is what we call, in terms of algorithm, per player local AGD, where the players take some steps of their own information using their own strategy, and they only communicate with other players only few times every number of iterations. This is the variant that some of you might know. If you are expert in federated learning, we have Fed averaging or local AGD. This is the corresponding in games and multiplayer problems, where now the communication is not a gradient, is the strategy that you have as a player. And we have different scenarios that this works. I will not focus on anything. I will close now. I wanted to just share this idea of try to reduce the communication between players to reach the equilibrium as we did before. So before we care about iteration complexity and performance of the methods, now we care about communication complexity and how the players can solve the problem using their own methods that we explained, stochastic extragradient or stochastic gradient descent ascent. But now they can do that with less communication between the players. And we try to understand what is the minimum number of communications to reach the equilibrium in an efficient way. Okay, so I will stop here and feel free. I will be very happy to answer any further questions that you might have.
It's just. Yeah, so so some of the questions actually answered in the slides about your future work with constraints. I think that's kind of interesting to see.
Mhm.
I was also wondering, other than extra gradients, because you have this optimistic gradient descent ascent. Well, the first question is, can you do that? Can you, or is this already included in your framework if you follow that framework?
Yes, so we have the first part that it was related to the different stochastic reformulation and different sampling strategies.
Right.
We have for both extra gradient and the optimistic
So
method.
it's a more general framework.
Yes, it's more general that we have for different algorithms, and we explain how all of them can obtain the deterministic as special case, and also at the same time the step size, the sampling strategy, the mini batch size are controlled.
Okay.
They require different analysis, but we have for both methods. The second part is related to the shuffling. We only have it at the moment for the stochastic extra gradient that requires 2 evaluations in every step. And we are working on the optimistic setting, but in that scenario is more challenging to analyze. It's not as simple as the previous setting. So this shuffle of the data affect a lot the optimistic variant of the algorithm.
And the other question, general question, is that you have, you also mentioned in the beginning that there's another aspect of it, which is the gradient complexity, right? So you have a variance reduced version of it.
Yes,
Okay.
yes, that's
So
correct.
how do you put that into your framework? Is that
Yes, so for the gradient descent ascent part that I didn't cover explicitly in this work, we have the variance reduce already implemented, and we explain how all of them are affected. And with the variance reduction, we're able to control the neighborhood of conversions and make it disappear, because the method is a variance reduced, so we don't have any neighborhood. In the extra gradient, there are other papers doing that, but all of them focus on the uniform sampling. We were aiming to have a more general analysis that captures the variance reduction as well, but at the moment we do not have that.
Got it.
Okay.
Thank you.
Yes.
Yeah, thank you so much for this talk. Do you have any general rule of thumb for training a minimax game for deep learning practitioners?
Yes. So in deep learning, what practitioners do blindly, if they have minimax problems, they use gradient descent ascent in the stochastic regime. mini batch gradient descent ascent. Now the problem works. So if you run gradient descent ascent, you will solve the problem and might generalize well. But the method itself, it does not find an equilibrium. We know that gradient descent ascent only being able to solve very special structural problem. It might be strongly convex, strongly concave. If you or some non-convex, strongly concave. We have access to this and we know how you can implement it. But if you go to deep neural network, that everything is non-convex, non-concave, then we know that gradient descent ascent will not converge. Even if practitioners using it, and they might have good generalization performance, the point that they find has implicitly has nothing to do with the equilibrium because you don't solve the minimax problem. You converge to a point that we don't know exactly how it looks like, but it might be related to equilibrium or not. We don't have an answer to this. Now, if you use extra gradient or optimistic method, you might solve the problem and you know that at least the point that you will find will be related to the equilibrium that you originally aimed to solve because the method converge. So that's the only part. I think both of the extra gradient and the optimistic method has negatives in terms of implementation. The extra gradient requires double the number of gradient evaluations in every step. The optimistic method requires to save the previous gradient evaluation and use it in your update rule again. So these are, I think, the drawbacks of why potentially practitioners will not use these methods because are more expensive than gradient descent ascent. But the methods themselves converge to equilibrium for more general problems than strongly convex, strongly concave. So I think eventually, if we have an efficient implementation of the methods and we have the resources of running them, most likely the extra gradient variance will extensively be used because you know that they will converge to equilibrium. Even if at the moment, practitioners, they do not use them. So that's my, yeah.
So just my follow-up comments about this point. Yes, I think that's a very good point because, for example, the example you gave in training gun,
Yes.
It's obviously a minimax problem, and I mean practitioners are not exactly using the alternating descent ascent. In fact, it's asymmetric word.
Yes, that's correct.
They take the descent multiple steps and then they make one single ascent step. So, but yeah, I think end of the day, they probably are not finding any stationary point.
They don't.
At all. And I think that's the reason why, when the diffusion model came out,
Yes, that's
people
correct.
just all moved to diffusion models because, at least there we are doing minimization and
Yes.
we don't need to worry about, the dirty thing about, training guard. So, but yeah, I would say overall, yes, practitioners are still feel very scary about minimax problem.
I think so. I think so. And we try to provide at least some answers on this direction for us to be, and practitioners, your point, to make their life hopefully more easier in the future. But at the moment, they use methods that most likely they do not find a stationary point or an equilibrium. And we try to understand why this is happening and how we can make methods more efficient for achieving this goal. Yeah.
Well, it's monotone AI.
Yeah.
The finite side. You can have various things to have capacity for it.
Yes.
But then you wanted to have this kind of this component you have to and not only use but also you have to use the various function for finite side monotone.
Yes.
Monotonic and monotone AI. But I'm wondering for this is non-monotone.
Yes.
You use a stochastic difference. You use like a very good way. Whether you could use like incorporate some like these variants about
yes. So
improve the overall operation cost, not just
yes, I agree. So there are papers doing that, but I think the variance reduction is not. Okay, for the examples that I mentioned, this fast strongly monotone or potentially infinity, one might come up with variance reductions that work in this scenario. I think there are some papers doing that, But I think the fact that you assume finding some structure for having a variance reduced method, or the fact that this cannot extend easily to the non-convex, non-concave setting, I think from practitioner's viewpoint, I don't think that anyone will run variance reduction. But from theory, I appreciate that this is very valuable step on understanding what is happening. But I doubt that someone that trained guns, for example, or adversarial training will actually run a variance reduced method. I think this is very expensive and very complicated to actually implement. Okay. Thank you very much.
Any more questions? Now let's thank the speaker again. Okay.
Thanks. Thanks a lot. Yes, sir. Thanks. Thanks for coming. Yeah.